I want to take a look at this question. It's rather easy, so read the question and just follow along. We're trying to find the A and B, and we'll start with a free body diagram first of the metal plate AB with a force pushing this way, that's P, and we have two rubber sides that's resisting it, which gives off a shear force in both directions of the same magnitude. And we know that from statics, P must equal to twice V. If we look at this from a 3D point of view, it's even more obvious that's the case. We have force acting this way, which is the shear force from the rubber. And on the other side, we also have the same rubber that acts this way and a P that push in the axial direction. Okay, we know that P is 45 kilonewtons and it is equal to 2 shear force. So one shear force must be 22.5 kilonewtons. We know that shear stress, tau, is equal to shear force over the area. What's the area then? The area is the surface, what happened? Whoops. Is the surface area of the rubber pad that contacts the metal plate. So this dimension will be C and this dimension will be B. This entire area will be providing the shear force going that way, which means 22.5 kilonewton shear force is applied over an area of B times C. We know that C is 100 and we're trying to solve for B, so I will just write it as 100B. What is this equal to? B can be any number, but in this case, we're trying to find the smallest B so that the stress does not exceed 1.4 megapascal. So we'll set the maximum, which is 1.4 megapascal, and we'll solve for B. To make units consistent, we'll have to convert kilonewtons to newtons, and 100 millimeters times B in millimeters can stay the same. Then do the math, we'll find B is equal to approximately 160.7 millimeters. That's answer 1 out of 2. Next, we'll find A, and we'll have to draw another free body diagram, or rather displacement diagram. This is the top view of the deformed rubber. Deformed rubber top view. And the dotted lines are its original dimensions. We know the height over here will be the dimension that we want to find, which is A. We know the dimensions here is B, but that's not really useful to us, so I'll ignore it right now. What's really concerning is the offset caused by the shear force, which I will call delta. And the change in angle here, pi over 2 minus shear strain, and that's just shear strain, gamma. Okay, that looks like an R, but it's gamma. We know what the displacement is at its maximum. I mean, the minimum, which is 5 millimeters. So sigma is 5 millimeters. And we'll use the Pythagorean theorem. Actually, I mean, basic trigonometry to find out what A is by drawing the relationship that tangent of gamma is equal to delta over A. Now, what is gamma? Gamma is the shear strain, and we can recall from Hooke's law that G, the modulus of rigidity, is tau over shear strain. Tau is again shear stress, which we just found. I mean, we didn't find, it was given. It was 1.4 megapascal over the unknown gamma, and that is equal to the modulus of rigidity, which is 12 megapascal. Now, if I just swap the positions between gamma and G, I would get that gamma is approximately 0.116 repeated in radians. Okay, now we have what we need, all we need to solve A. And we'll go back to the tangent relation, which I'll just pull down right here. That is equivalent to saying tangent of 0.116 repeated in radians is equal to 5 millimeters over A. Solve for A, and you will get approximately 42.66 millimeters. Now that's our answer, but doesn't it look a little strange? 42.66, that's 8 times more than the 5 millimeter displacement. But it does make sense if we draw out how it will actually look. We know the gamma is 0.116 radians. That's approximately 6.8 degrees. And that's a very small angle. In order to have a 5 millimeter opposite, you do need a very large adjacent, which would make sense. So from that point of view, this is the correct answer. Therefore, A minimum is 42.66 millimeters. B minimum would be 160.7 millimeters. And there you go, that's our answer.